Okay. Yeah, so today we're going to have a lottery, and here are the prizes. Yeah, yeah. So the prizes are all the books that I have written. Yeah. All right. So yeah, today I want to do a few examples, of how to use the spectral sequence to calculate the cohomology of various objects. And the first example is the unitary group. Okay. So the unitary group UN is defined to be all complex matrices, non-singular complex matrices, such that A transpose A is the identity. Right? It's a very important group in mathematics and in physics. It's a Lie group, so it's a manifold as well as a group. Now, the unitary group acts on Cn by matrix multiplication. Okay? So A dot X is just AX, where A in the unitary group and X in Cn. And this action takes the sphere to the sphere. It takes the unisphere to the unisphere. This action takes the unisphere will be S2m minus 1 to S2m minus 1. Okay? So because if X is in S2m minus 1, which is in Cn, then it just means that the norm of X is 1. Right? So the norm of X, is X, X conjugate transpose X. And if you have so this is supposed to be 1. And if you have a unitary matrix, the norm of AX square is AX transpose conjugate AX, and that is X transpose conjugate. The transpose reverses the order. Okay, and this is the identity by definition because A is a unitary matrix. Yeah. So basically, the unitary matrix preserves the length of a complex vector, and therefore it takes Sn2m minus 1 to itself. And you can show that this action is transitive. Okay, so this is a homework problem. So this action of UN cross S2m minus 1 to S2m minus 1 is transitive. Transitive means that there's only one orbit. Okay, so there's only one orbit. Okay, so there's only one orbit. Okay, so this action of UN cross S2m minus 1 to S2m minus 1 is transitive. Transitive means that there's only one orbit. Okay, so there's only one orbit. Now the orbit consists of all the points that you get from one given point by applying the group. So only one orbit means that for a fixed P naught in S2n minus 1, given any P, well, let's see. Yeah, given any P in S2n minus 1, there exists an A in the unitary group such that A applied to P naught is P. Okay? Yeah. So every point is in the orbit of a fixed point P naught. And another thing I want you to show is that the stabilizer, okay, of E1. Okay? Now E1 is the unit vector. Okay, so it is in S2n minus 1. And I want you to show that the stabilizer E1, that's all the unitary matrix that take E1 to E1. It's of this form, 1, 0, 0, 0, 0. And then there's a smaller unitary matrix here. So B is in U n minus 1. Okay? So that's a homework problem that this action has only one orbit and the stabilizer is U n minus 1. Okay? Now we have the orbit stabilizer theorem. So the orbit stabilizer theorem says this. It says, yeah, so like you have this map. So suppose, a group G acts on manifold M, okay? And this is a Lie group. Everything is C infinity. And then you have a point P naught in M. Then you have a map from G to M, okay? By sending G to G P naught. Okay. So actually, yeah, this map will go to the orbit of P naught. So orbit. Okay. And if you have a stabilizer of P naught, yeah, so a stabilizer P naught will just go to P naught. Right? So let me see. Yeah. So like you can define a map from G over the stabilizer of P naught. Okay? So because okay, if we let H be the stabilizer of P naught, then you see GH will map to this same thing, right? Because GH will map to GHP naught, but H is in the stabilizer, so this is the same as GP naught. Okay, yeah. So you have a well-defined map from the cosets okay, to the orbit of P naught. Okay, you've got this well-defined map from G over the stabilizer of P naught to the orbit of P naught. And then, so yeah, so then this map is a diffeomorphism. Okay, so that's the orbit stabilizer theorem. Yeah. Okay, so let's apply the orbit stabilizer theorem to the action of UN on the sphere. And so what do we get? So we get, let's see, so apply to G equal to UN and P naught in S2N minus 1. So we get UN, okay, we get G over the stabilizer of P naught. It's UN over the stabilizer. Oh, yeah. Let's not use P naught. Let's just use E1. Okay, and the stabilizer of E1 is UN minus 1. Okay, and then we get a diffeomorphism to the orbit of E1. But the action is transitive, so there's only one orbit. The whole thing is an orbit. So this is S2n minus 1. Okay? So in this way, we write an odd sphere as a quotient of unitary groups. That's called a homogeneous group. And you know, there's a theorem about a quotient of a Lie group by a closed subgroup. Okay? So the theorem says, and this is from manifold theory, if H is a closed subgroup of a Lie group G, then you have a natural projection map pi from G to G ma H is a fiber bundle with fiber H. Okay, so what it means is that this map is locally a product of an open set with the fiber H. And so therefore, so we have a fiber bundle. UN maps to the quotient, which is S2M minus 1, and the fiber is UM minus 1. Okay? So we have a fiber bundle. And we want to calculate the cohomology of UN. We can do that when you have a fiber bundle. You can apply the Leray spectral sequence to this fiber bundle. Okay? And the Leray spectral sequence will give you the cohomology of the total space in terms of the cohomology of these two, the base and the fiber. Okay? And so you can calculate the cohomology of UN by induction. You calculate, the cohomology U1, and then this fiber bundle gives you the cohomology of U2, and you apply the spectral sequence again to get the cohomology of U3, and so on. Okay? So okay, so let's start with U1. Okay, U1. What is U1? All right, so today I want to do the cohomology of U2, and then in the homework, you do UN. Okay, so, and to do the cohomology of U2, we start with U1. Okay. So U1, by definition, is a 1-by-1 complex matrix. So it is just a complex number, and it has non-zero determinant. That means it's not zero, so it's in C star. Okay? C star is the non-zero complex numbers. Okay. And it satisfies Z conjugate transpose Z is the identity, and that just means that it has unit length, right? So what is U1? This is just to test whether you are awake. It's, what is U1? Come on. Yeah, it's the unit circle, right? It's complex numbers of unit length. It's S1, okay? So we already know the cohomology of U1. Okay, yeah. So it has 1 in dimension 0. The generator in dimension 0 is 1, constant functions. And in dimension 1, okay, it has a generator, right, a closed one form that we call X. Okay? And okay, so we have the Leray spectral sequence for a map. And so the Leray spectral sequence says that um, um, yeah, when you have a fiber bundle, so we have this fiber bundle, U2 mapping to, what is it? Oh, yeah, just a minute. For U2, okay, N is 2, okay? So the sphere is S3, okay? U2 maps to S3, and the fiber is U1. So we have this fiber bundle. U2 maps to S3, and the fiber is S1. So we have a fiber bundle. Okay? And so the Leray spectral sequence is that, then there is a spectral sequence, and it gives you the U2 term. Okay? And then under this special hypothesis, if you have a fiber bundle and the base is simply connected and the fiber has finite dimensional cohomology, then the E2 term is a tensor product. Okay, so for a fiber bundle, so with fiber F, total space E, and base M, so if M is simply connected and let me see, and the cohomology of F is finite dimensional, you actually need finite dimensionality for each Q. Well, okay. Yeah, but we're in the C infinity category, so the dimension of the cohomology cannot go to infinity anyway. So yeah. So the cohomology F is finite dimensional, then the Leray spectral sequence, which is the spectral sequence of the double complex of the total space, has E2 EQ equals HP of the base tensor with HQ of the fiber. Okay? So that's Leray's theorem. And okay, so in our case, then this is the E2 term. Well, so the bottom row, that's when Q is 0, E2P0 is HP of M tensor H0 of F. So if F is connected, then it's just HP of M, okay? For F connected, yeah, okay? So the fiber S1 is connected, and that means in the bottom row, you just have the cohomology of S3. So we know that already, right? The cohomology F3, that has stuff in dimension 0 with generator 1. And then in dimension 3, you have a closed 3 form, Y. And so similarly, this 0th column is the cohomology of the fiber. Okay? So let's write that. If M is connected, yeah. So this column is the cohomology of S1. This row is the cohomology of the base S3. Okay, so we know that for S1, you have something here in degree 1. Okay? And then everything else is 0. Okay? And since it's a tensor product, okay, if these two are 0, all the columns are 0. All the rows are 0 there, all the columns are 0 here. So yeah, E2, okay, let's fill in E2, but it's 0 here, 0 here. That means it's 0 here, 0 here, okay? And here, you know, that's R tensor R, so it's R. And the generator would be X tensor Y. Okay? And we'll just write that as XY, okay? I omit the tensor. This XY, that means X tensor Y. That's E2. And in the spectral sequence, okay, as you turn the page, right, eventually, you know, it stabilizes, and that's E infinity. And E infinity is supposed to be the associated gradient of the total space. So this converges to E infinity is the associated gradient complex of the cohomology of E, but we're using real coefficients. So the associated gradient complex is just, you know, the cohomology itself. Okay. Okay, so what we need to do is now we have the second page, and now we just turn the page. And eventually you will end up with the cohomology of the total space U2. Okay? Okay, so how do you get the next page? The next page is E3. And so you have to look at the differential D2. Okay, and so you have to see where this goes. Okay, which box does it go into? I mean, how many, yeah, how many boxes does it go down and across? Okay, tell me which box it goes into, D2. I mean, yeah, so, you know, I want to write down an arrow. Where does it go into? I mean, D2 goes, okay, just tell me what D2 does. Yeah, it goes 1 down and 2 across, okay? So D2 is gonna go 1 down and 2 across, so it goes here. And we are so lucky because this box is 0. So D2 is 0, okay? And yeah, and this one goes down and across Well, of course, it will go to 0 because it goes down, right? That also goes to 0. This one goes down 1 across 2. Okay, yeah. So you see the D2 is 0 on E2. And that means E3 is the same as E2. Okay? So, yeah, we are lucky because usually you have to turn a few pages, before the picture stabilizes. But here it stabilizes at E2. So let's see. Let's write this down. So since D2 goes down 1 and across 2, from the picture, you can see that it's 0. Okay? So therefore, E3 is the cohomology of E2 with respect to D2. It will be the same as E2. Okay, so this is a picture of E3 as well. But then D3 is even more 0, right? Because D3 will go down 2, and that will be in the 0 region. Okay? So D3, D4, D5, D6, they're all 0. Yeah, so similarly, D3 equals D4 equals D5. They're all 0. And so E2 equals E3 equals E4. And that's E infinity. It stabilizes. And E infinity is isomorphic to the cohomology of U2. All right? Okay. So this is the cohomology of U2. It's got one element, one non-zero element in degree 0, degree 1, degree 3, and degree 4. Okay. Okay. But we also know how the generators multiply because we know that degree 1 times degree 3 will give us the generator in degree 4. So thus, HK of U2 is R times 1 for K equal to 0, okay? And then R times X for K equal to 1, R times Y, K equals to 2, and R times XY for K, Y is in degree 3, and XY is in degree 4, and then it's 0 otherwise. Okay, but as a ring, it's generated by X and Y. And then x squared is 0, right? We have no x squared. So we have to set x squared equal to 0. Y squared has to be 0. There's no y squared. Okay. Yeah, you have xy. Oh, well, yeah. Okay, no, I shouldn't write it as a polynomial ring because a polynomial ring is commutative. Uh, yeah, so but this is not commutative because xy, right, is minus yx, since x is a 1 form and y is a 3 form. Okay, so what can I write? I guess I'll write this, but I don't mean the rational expressions either. So I'll write where r of xy is the free algebra generated by x and y. Okay, so I'm not writing the polynomial ring because the polynomial ring assumes that it's commutative. So is the free algebra generated by xy. That means you just write down all the expressions, xy, like, so it will have xy, xyx, yx, and okay, so let's say xxy. So these three are not the same in the free algebra. The free algebra, it's just like you write down all possible expressions that you can get by multiplying the elements together, but you don't assume that it's commutative. But in this case, we know that xy is minus yx, so it's anti-commutative. And so you need a relation, and the relation would be xy plus yx is equal to 0. Right? So that says xy is equal to minus yx in the quotient ring. Yeah, so this would be the ring structure. And yeah, and then there's a notation for this. When you have like a free algebra with some generators, and the generators graded commute, then it's called the exterior algebra. Okay? So this is the exterior algebra generated by, x, y in degrees 1 and 3. Yeah. So in general, okay, let me define the exterior algebra with many generators. But let me first put the answer in a box. So this is the answer. This is the cohomology of U2. Well, so we should say the cohomology ring of U2 is this. Okay. And so the definition of the exterior algebra with many generators is that it is the free algebra, okay, mod out by an, an ideal, okay, and the ideal simply tells you how to commute any two of them. So xi, xj, yeah, it should be equal to, when you commute them, it should be -1, the degree of xi times the degree of xj, xj, xi. Okay, so these two should be equal in the quotient, and that means you mod out by this minus that. Okay? And you see here, okay, we say x squared is 0, but that really comes from xx, and then when you commute them, because it's odd, it's going to be minus xx, and so you have to subtract, and so you get x squared. Okay, so in fact, yeah, to say that x squared is 0, well, it's just a special case of this relation. Yeah. Okay. All right. So this is the exterior algebra with generators x1 to xk, and they can have even or odd degrees. Okay? Yeah. Okay, so in the homework, you calculate the cohomology of xn. Okay, now I want to do another example. An example that's not a fiber bundle. Okay, now to set up the example, yeah, let me just talk about the nerve of an open cover, and then we can take a break. So the nerve is, okay, it's a graph, or it's a generalization of a graph. And that's called a simplicial complex. Okay, so let U be an open cover of a topological space X, and to get the nerve, so to every U alpha in U, we associate a vertex. Okay. And then if U alpha intersect U beta is non-empty, then that means that you connect the two vertices, by an edge. So a vertex alpha connect alpha beta by an edge. Okay. And if a triple intersection is not empty, okay, then you fill in the triangle, okay? So, okay. If the triple intersection is not empty, then the pairwise intersections are not empty, okay? So you will have alpha, beta, gamma, and then you have this you have these three edges, and so you fill in the triangle. And if the quadruple intersection is not empty, okay, then you will have, like 4 triangles, right? Yeah, right. Yeah, 4 choose 3. That's 4. You get 4 triangles, and they are the faces of a tetrahedron. So you fill in the tetrahedron. Tetrahedron. Right? So in this way, you get what's called a simplicial complex, and that is the nerve of the open cover. Okay? So, so you associate to U, N of U, which is a simplicial complex. Yeah, and so so instead of drawing the open cover, it's a lot simpler just to draw a simplicial complex. Okay. Yeah, so let's see. Let's look at an example. Oh, yeah, so like if you have an open cover like this, U alpha, U beta, U gamma, then the nerve would be this. So if this is U, then this is the nerve of U. And then if you have a pre-sheaf, if you have a pre-sheaf, on the open cover, it associates to each non-empty intersection a group. And so a pre-sheaf would be, at this point, you have, you have F of use of beta, and then here you have F of U of gamma. You put the group here, F of U of alpha, and then on this edge, you have F of U of alpha gamma. On this edge, you have F of U of beta gamma, and then F of U of alpha beta, and then F of U of alpha beta gamma, okay? So a pre-sheaf F on U would be represented by a picture like this. Yeah? You draw a simplicial complex, and then you put various groups on the faces of the simplicial complex. Okay, we're going to take a break. for 10 minutes. Okay, so what we're going to do now is to use the Leray spectral sequence to compute the cohomology of a circle. Okay? Now, you already know the cohomology of circle, and it's not that difficult to compute. But the reason I want to do this example is to use the Leray spectral sequence to compute something that you know the answer of already, so that you know that the answer is right, Because okay, we computed the cohomology of the unitary group and we got an answer, but maybe it's wrong. Who knows? Yeah, so in English, this is called to use a hammer to kill a fly. Yeah. So is there like a Chinese expression for that? Huh? Oh, 杀鸡用牛刀啊. Uh-huh. Okay. Yeah. Very good. Uh-huh. But it doesn't seem so extreme, right? To kill a chicken with an ox knife. Yeah. Yeah. Is there something more extreme than that? Yeah. Because like to kill a fly, I mean, you don't need a hammer, right? A hammer is too big. Yeah. There's an expression in Chinese for everything. Yeah. Yeah. Okay, maybe 杀鸡用牛刀 is the best. Thank you. Okay, so let's consider this projection, okay, of a circle, down to an interval. Okay, so this takes xy to x, and the interval is -2 to 2, and this is the unit circle. Mhm. And we're going to cover the interval with 3 open sets. Uh-huh. Okay, so so what are the 3 open sets? It's going to be, let's see, so from -2 to -1/2, and then from 1/2 to 2, okay, and then from -3/4 to 3/4. Okay, so these are the 3 open sets. And I will call them U0, U1, U2. Okay. So the open cover is U0, U1, U2. That's an open cover of I. And U0 is -2 to -1/2. U1 is -3/4 to 3/4. And U2 is 1/2 to 2. And we want to compute the cohomology of the circle by Leray's method. So Leray invented his theory of spectral sequences in the 1940s when he was in prison. Okay? Because during World War II, Germany invaded France. And Leray was in prison. I forget for what reason. Either he was imprisoned by the Germans because he fought for France, being patriotic, or maybe he didn't want to fight, and so he was imprisoned by the French. So you have to, look in Wikipedia to see why he was in prison. But anyway, he was in prison, but it turned out that it was really good for him because he was just doing mathematics and he did his best work in prison. Yeah. So later, like I was told this. He gave a talk, at the Institute for Advanced Study in the United States, and by then he was quite old, and he made a mistake, on the blackboard. Yeah. And there was a mathematician, Andre Leray, in the audience. And so Andre Leray thought that, well, Leray did better work when he was in prison. He's now making mistakes. So Leray said, you should go back to prison. Okay, so Leray's method is to compute the cohomology of this total space using the Czech-Deram complex, using the spectral sequence of the Czech-Deram complex of the open cover that you get by taking the inverse, right? So it's the Czech-Deram complex of pi inverse of U. Okay, this map is pi with coefficients in the differential forms. Okay, because we know that, right, yeah, this is a double complex. To the cohomology of S1. Okay, so and we know that the E2 term, okay, yeah. So his theorem, the Leray spectral theorem says that the spectral sequence of this double complex of K converges to the cohomology of S1 with E2 PQ equal to, well, it's not a tensor product like in the previous example because there we had a fiber bundle. Okay? So here it's the Czech cohomology of the open cover U downstairs with coefficients in the cohomology sheaf, right? Where this cohomology sheaf of U is HQ of pi inverse of U. Okay, so what we need to do is first to calculate the cohomology sheaf, this, okay? And let me see, so we got these three open sets, and then we have some pairwise intersections. Okay, so we can represent it by its nerve. Okay, so we got three open sets. Okay. 0, 1, 2. And then 0 intersects 1. Okay. And 1 intersects 2. But 0 does not intersect 2. Right? Yeah. U0 does not intersect U2. And so there's no edge from 0 to 2. Therefore, you don't have a triangle. Okay. You only have 2 edges. And yeah, so this is the nerve. This is the nerve of this open cover. And we have to calculate HQ. Yeah, so let's look at the inverse image. Okay. Yeah. Now, for U0, well, you've got this, right? That's the inverse image. It's an arc. For U2, the inverse image is also an arc. Okay. But for U1, the inverse image consists of 2 arcs. Okay. Yeah. So they're all arcs. They're all one-dimensional, and that means there's no cohomology above degree 0. So we only need to look at H of 0. So let's see. So H of 0. So we need to calculate H of 0 of pi inverse U0. That's going to be HQ of U0. Okay, HQ of U1 is H0 of pi inverse of U1. And then you have 0, 1. That means the intersection of U0 and U1. All right, so we need to calculate these 5 homology groups. Yeah. Okay, so what is H of U0? What is that? Well, just an arc. So it's, okay, I don't want to wait for the answer because it takes too long. But okay, and how about this? Tell me what this is. Quickly, R2, yeah. Because you have 2 arcs for U1. For U2, you have R. Okay, 0, 1. 0, 1 is this part. So what is that? Yeah. Hey, somebody other than Su Pingchen should talk, okay? R2. Okay, yeah. You know, you are not being filmed. Only I'm being filmed. So if you give a wrong answer, nobody knows. Yeah. What is 1, 2? R2, good, yeah. Okay, yeah. Okay, so so our pre-sheaf is R here, R2. Okay, let's put it here. R2, R. And then yeah, 0, 1 is R2 and 1, 2 is R2. Okay, that's a picture of our pre-sheaf, H0. Okay. And yeah, so so we I mean, we first compute, let's see, yeah, E1. Okay, I mean, E2 is going to be the cohomology E1, okay? To write down E2, you have to calculate the check cohomology anyway, and that's just the cohomology E1, so we might as well just write down E1. So E1 of PQ is HD of PQ of K, okay, and it is, so it's just going vertically, right? Because this is K, and if you take HD, you just get the cohomology HQ of pi inverse of U alpha 0 alpha P, okay? And that's what we have calculated already. Okay, so so E1 looks like this. Let me see. So E1, okay, so here we should have this plus this. No, this, yeah, it's the cohomology of the three open sets, right? So it's going to be R plus R square plus R. Okay. And then we have the pairwise intersections. That's R square plus R square. Okay? And everything else is 0. Okay? So that's E1. And then we have this map delta, which is the alternating difference. Okay, okay, so this R is the cohomology over U0, this is over U1, U2, this is over U01, U02, okay? And so we can write this as a real number B, and then a vector C1, C2, and a real number D, okay? And then take the alternating difference. So here it would be restriction from 1 to the intersection minus restriction from 0 to the intersection. So it's going to be C1 minus B. Okay, B restricts to B on both components, right? C2 minus B. Okay, that's this. And then here would be, let me see. So it would be D minus C1, D minus C2, okay? So that's the map delta. And then, so we need to take the kernel of delta. That will give us the cohomology in this box, E2, right? So the kernel of delta means that it's all B, C1, C2, D, such that set all of these equal to 0. So C1 equals B, C2 equals B, C1 equals D, C2 equals D. Okay? So that means B, C1 is B, C2 is B, but D is C1, so D is also B. That's the kernel of delta. So that's R. Okay? Yeah. And right, so like E2, so E2 of this box, 0, 0, it is the cohomology of this, and that's just the kernel of delta, because there's nothing coming in. So it's kernel of delta. So that's R, okay? And E2 of the next box, 1, 0, that is going to be the cohomology of this box. So it's the kernel of this map. That's everything. Over the image of delta. But the kernel of delta is R. That implies that the image of delta is R plus R2 plus R over the kernel of delta. So R4 over R, and that's R3. That's the image of delta. So here you have R4 over R3, and that is R, okay? Okay. Okay, so now we have E2. So E2. E2 is the cohomology of E1. And it is this R here, 0, 0, 0, 0, 0, 0. That's E2. And this, and then D2 is obviously 0, D3 is 0. This is E infinity. So this is E infinity because the spectral sequence degenerates. Okay, so this is E infinity. And E infinity is the cohomology of S1. Okay, and so you see that in degree 0, you've got R. In degree 1, you have R. And in all other degrees, you have 0. Okay. Yes. It's good that it turns out to be correct. Okay. That's so our final conclusion is that all right. So I hope this gives you some confidence in Leray's spectral sequence. Okay, and so I'm going to turn the microphone off.